mixing chambers. Okay, mixing chambers, it has three parts. 1, 2, 3. These two part is the inlet of the mixing chambers, and this part is the outlet of the mixing chambers. The fluid will flow. The fluid of different temperature will flow into the chambers through this part and this part, and it will flow after it mixing in the chambers. It will flow through the outlet. Now, I'm going to show you how it goes. The section where the mixing process takes place. The T elbow and Y elbow serve as the mixing chambers for cold and hot water streams. Now, for the derivation of the equation of mixing chambers. Firstly, the conservation of mass in adiabatic mixing chambers in steady flow. Okay, this is the general equation of the conservation of mass in the rate form, which is summation of m dot system equals to summation m dot in minus summation m dot out. But for steady flow, the summation of m dot system will be 0. So the summation of m dot in will be equal to summation of m dot out. The mixing chambers are well insulated. The work, potential energy, and kinetic energy are negligible. The combinations of both mass balance and energy balance equations are we already know that Q dot in will be cancelled out. Q dot in and Q dot out will be cancelled out because the mixing chambers is the adiabatic. Then the work dot in and W dot in, W dot out will be cancelled out because the work is approximately equals to 0. And then the theta equals to H plus V square over 2 plus GZ. Okay, GZ is the potential energy and the V square over 2 is the kinetic energy. Now, as we substitute this equation into the equation above here, we get this one. We get the last equation, which is the summation of m dot in H in equals to summation of m dot out H out. Now, examples of problem solving. Now, I'm going to read the question first. Liquid water at 300 kilopascal and 20 degrees Celsius is heated in a chamber by mixing it with superheated steam at 300 kilopascal and 300 Celsius. Cold water enters the chamber at a rate of 1.8 kg per second. If the mixture leaves the mixing chamber at 60 degrees Celsius, determine the mass flow rate of the superheated steam required. Now we transfer the picture into a simple diagram so that we can be easily find the M2 here. Okay. Given that at point 3, P equals to 300 kilopascal, T3 equals to 60 degrees Celsius. So at point 1, T1 equals to 300 degrees Celsius. And 2, you are going to find it. And at point 3, T2 equals to 20 degrees Celsius. M2 equals to 1.8 kilogram per second. Solution for example 5. Firstly, apply mass balance equation and label the outlet and inlets. This is the mass balance equation. Generally, and it is equals to 0, the m dot system equals to 0 because of the steady flow. And then at last we get m dot into the system will be equals to m dot out of the system. Okay. Second, apply energy balance equation. Okay. The steady flow, the energy rate of energy in the energy balance in the rate form of the system will be equal to 0. So as we know, summation of E dot system equals to summation E dot in minus summation E dot out. So as the summation E dot system equals to 0, the summation of E dot in will be equal to summation E dot out. Third, apply combine mass balance equation and energy balance equation. So we are going to apply the energy balance and also the mass balance equation. And this one point for the point 1, this one for the point 2. Point 1 and point 2 is the inlet. Point 3 is the outlet. Then point 3 is where the M1 mass from point 1 and mass from point 2 mix will be, and become mass 3, mass at point 3. So mass m dot 3 will equals to m dot 1 plus m dot 2. So we substitute m3 equals to m dot 1 plus m dot 2. Last, as the question requires the mass flow rate of the superheated steam, we look up to the number 2 inlet, the hot water stream. So m dot 2 equals to enthalpy 1 minus enthalpy 3 minus enthalpy 2, multiply m dot 1. Now, we are going to analyze the properties of water at the chamber. The water that flows into the chamber are superheated steam and liquid water. The superheated steam and liquid water will be mixing in the chamber at pressure 300 kilopascal, and then it will flow out the mixing chamber and the temperature will be 60 degrees Celsius and the pressure the same, 300 kilopascal. Now, we are going to find the properties of the saturated mixture here. Firstly, we refer to the table saturated mixture at pressure of 300 degrees Celsius. We can see that the saturated temperature is equals to 133.52 degrees Celsius. So, the temperature of saturated is bigger than the temperature of the mixture, which is 60 degrees Celsius. At point 2, is liquid water. At point 3 is mixture. We assume that at point 2, we are not going to assume, but we can say that at point 2 and point 3 is approximately exists as saturated liquid at given temperature. So we are going to find the properties, which is enthalpy for liquid, the mixture at point, enthalpy for point 3 and so enthalpy for point 2 through the table of saturated water. Firstly, we refer to the temperature. Okay, at 20 degrees Celsius, the saturated liquid equals to 83.915 kilojoule per kilogram. Then, for the mixture at the outlet, 60 degrees Celsius, we refer to the temperature, and then we're going to find the saturated liquid enthalpy, the enthalpy for saturated liquid. And then we found that this enthalpy for H3 equals to 251.18 kilojoule per kilogram. Given that at point 1, the superheated steam, the T given equals to 300 degrees Celsius, and the P given is 300 kilopascal. Now, we are going to refer to the table A6, which is the table of superheated water. For the pressure given 300 kilopascal or 0.30 megapascal, and T given equals to 300 degrees Celsius, we are going to find the enthalpy. Through here, the enthalpy is 3069.6 kilojoule per kilogram. In order to find the mass flow rate at point 2, we need to apply the mass balance equation and also the energy balance equation. From the combination of these two equations, we get this equation. But we need to understand why m.1 plus m.2 equals to m.3. This is because at the point 3 is the flow of the water that mix from point 1 and point 2. So m.3 equals to m.1 plus m.2. We rearrange the equation and we get this one. As we get this one, we can substitute all the values. So the mass flow rate at point 2 equals to 0.17 kg per second. Heat exchangers. Heat exchangers is a device where two fluids moving without mixing. Heat exchangers typically involve no work interaction and negligible kinetic and potential energy for each fluid stream. Under steady operations, the mass flow rate of each stream flowing through a heat exchanger remains constant. The heat exchanger is well insulated or adiabatic, so the rate of heat flows equals to 0. However, if only one of the fluids is selected as the control volume, if only one of the fluid is selected as the control volume, the heat will cross the boundary and it flow as it flows from one fluid to another. So there is the presence of the rate heat transfer between the fluids. Examples of problem. A heat exchanger is to heat water with the heat capacity of 4.18 from 25 degree to 60 degrees Celsius at rate of 0.2 kg per second. The heating is to be accomplished by geothermal water with the heat capacity of 4.31 kJ per kilogram degrees Celsius, available at 140 degrees Celsius at a mass flow rate of 0.3 kg per second. Determine the rate of heat transfer in the heat exchanger and the exit temperature of geothermal. Now, from the diagram, we mark the inlet with at point 3 and point 1, the outlet at point 2 and point 4. The cold water is heated in a heat exchanger by the geothermal water. The geothermal water flow from point 3 to point 4 and the water flows from 1 to 2. The temperature of the water increases as it across the geothermal water. The given data for the cold water and then the geothermal water. Now we are going to find the temperature at the outlet for the geothermal water.